So this is the Mitesh Khapra's lecture videos, okay, lecture slides. So you can see here the input to the network is an n-dimensional vector, x1 to xn. The network contains L minus 1 hidden layers, in this case 2 layers. Finally, there is one output layer containing k neurons, k classes in fact. Each neuron in the hidden layer, an output layer, can be split into two parts. Okay, what are the two parts? They are the pre-activation and the final activation. Okay, what is this A1, A2, A3? Pre-activation. And this H1, H2, HL, they are the activation. Can you guess what are they? Anybody from the class? What is pre-activation and activation? Can you guess? What is pre-activation and activation? Can you recall what we learned pre-activation and activation? So for any neuron, pre-activation is this part, the summation part. Summation of some Wi, Xi. That is the pre-activation. And activation is a function. After you have to pass it through the function. This is the activation. So these activation functions we already learned so many: sigmoidal, tan sigmoidal, and all. Linear, and all kinds of functions is what we have learned. Okay. So now you look at the slide again. Each neuron hidden layer and output layer can be split into two parts: pre-activation and activation. AI and HI are vectors. The input layer can be called the zeroth layer here, and output layer can be called the Lth layer in this case. Okay. So here you can see the connections. These are all the Wi's and Bi's of the weight and bias between layers I minus 1 and I. Okay, any layer you can call this. Is I varying between 0 to L. That is 0 to L. How many layers totally are there? L layers, okay. So this is a connection. So clearly you can see how it's being connected like this. Okay. N equal to 3 in this case. You can see it, 2 hidden layers and now one output layer. That's L is equal to 3. The pre-activation layer at layer I is given by AI is equal to Bi plus Wi Hi1 at this point. The activation at layer I is given by Hix, G into AIX. The G is called the activation. For example, logistic, TANX, linear, etc. The activation, the output layer is given by f of x equal to HLX or ALX. So, is it all right? Are you getting the point? Whether the notations are clear? What is this GAI? Can somebody tell me? What is the GAI? G is nothing but the activation function like logistic, TANX, linear. At every layer we have that function. Okay. So this BI, WHA is linear combination. That's all. So this is the data. It's a kind of model we are looking at. Okay. Starting from the input, it goes on like a nested loop like arrangement. Okay. Every layer we have weights. Okay, those weights are going to act over the previous layer's input. So it's more like that. So these are all the parameters involved. Algorithm with gradient descent with back propagation. The objective loss function is like this. So we already seen this. Okay. Vector function. So this is a gradient descent learning rule. We already learned this. Mu weight equal to old weight minus learning rate times delta W. Bias equal to old bias minus learning rate times delta V. Okay, delta theta t is equal to this. So we are interested in computing for a small change in the weights, how much the loss function changes. What we learned in the last class. The set of weights you have, initial parameters. These are all the updated parameters. So for a bigger network, you'll be getting this will become huge. Okay. So we have so many weights. The big matrix you'll be getting, but we will not do that. Recursive way we can do this. So we can choose L theta and then we can choose the how to compute del theta, which is composed of this change in weights with respect to the L. Okay, so we'll go here. Here is employing a different loss function. Within squared error, we have cross entropy. Output actuation can be linear or softmax. We'll learn about softmax later on. Loss function in this problem he has used is cross entropy. It's a different kind of loss function. But let us try to see the what do you call it, step symbol. Yeah, this is the step symbol. So this is what is happening. The input side, the input is entering and it goes into the first layer, pre-activation, then activation, then goes to the second layer, pre-activation, activation, then finally. And finally you'll be getting the loss function, the error. So the chain rule is more like it. You have to remember this slide. Okay, this is a chain rule here. Dou L theta by dou y cap by dou AL1. Okay, then dou AL11 by dou H21, dou H21 by dou A21. Pre-activation, activation. See here very clearly. This is the output. This is activation. What is the pre-activation to it? Dou AL. So you're finding out the derivative with respect to that. And then the AL1 is being affected by H21. So you are taking AL1 by H21 and then H21 by A21, then A21 by H11, H11 by A11 and A11 by W11, W triple. So the final one, this one. Okay. So here this is the overall scenario. This is just compressing the chain. Take out all this, we will write this. Okay. So dou here del theta by dou W211 can be in a similar way you can write like this. For every node you can write like this. So this is a key idea. So look at this idea. We get a certain loss at the output. So this loss function is different. Okay, this loss function is called cross entropy loss function. We have not discussed it yet. We will discuss it. But right now, just imagine for intuitive understanding, if this is a loss function. We get a certain loss at the output. We try to figure out who is responsible for this. How do we do it? So we talk to the output layer and say, hey, you are not producing the desired output, better take responsibility. So this loss function is communicating to this final layer. Okay, better take responsibility. The output layer says, well, I take responsibility from my part, but please understand that I'm only as good as the hidden layer and weights below me. So naturally, the weights also responsible here. Below to that, in the main layer, they are also responsible. Okay, so after all, this is what the expression is. What is wrong with it? So now what they will say? They will say these are all responsible. The weights just below it, they are responsible. The pre-activation layer in turn says that I am only as good as the hidden layer and weights below. So naturally, it's going to come down. So that's why, in fact, we are talking to the we're talking to the weight. In order to talk to the weight directly, W11, for example, you need to come through all these layers. Dou L theta by dou y cap by dou A3, dou A3 by dou H2, dou H2 by dou A2, dou A2 by dou H1, H1 to A1, A1 to W1. So that's how it normally the chain rule normally operates. So we are trying to assign the credit to each and every one of the weight. It's called, that's why it's called as credit assignment problem. Okay, quantitative of interest. Okay, so that's how it works. Talk to the output layer, talk to the hidden layer, talk to the previous hidden layer, and now talk to the weights directly. So we will learn about cross entropy loss in a different class. Okay, so that's the intuition. Now I would like to show you one more slide. Should be of use to you. Yeah, here it is. The radiant enthalpy element. one hot representation is different from. Okay. So this is a lecture slide from CMU. Okay. CMU slide. Yeah. So this is how the network looks like. Okay, we have one hidden layer, one input layer, two hidden layers, and output layer. Okay. So at every layer, what's happening? We are adding the weights multiplied with inputs get inside. That's the pre-activation, and this is the activation. It goes outside. Okay, that's what's happening. It's clearly seeing it. This is the first hidden layer, second hidden layer, output layer. So it's more like each yellow ellipse represents a perceptron. Okay, each one is more like a perceptron. Coupled together in a multi-layered framework, we have a multi-layered perceptron like this. Okay. So now computing the derivative for a single input. Okay, for single input, you're going to compute the output. This output you call it as we call it as the divergence. Okay, so here it is the cost function is there. Okay, we would like to minimize the cost function based on this divergence factor. Okay. Is it all right? What do you understand from the slide? Anyone? Can you explain the slide? What is that understanding? We have a set of inputs, we have an output, it passes through the forward propagation manner, the single data has been passed, and every node, in fact, we are computing the pre-activation function, followed by an activation function like the log sigmoidal or tan H function, and then it goes up for the given set of weights and biases, you'll be getting the corresponding output, and you are computing the diverging error. Okay, this is the divergence. This is DIV is the divergence error they call it. Y comma D. It's a function of Y comma D. Desired output minus the output that comes out of the neural network. Okay. Then what do? You compute the gradient for the kth layer. Okay. Here is what's happening. Look at this. Okay. Just imagine this is first one. This is y of 0 equal to x for rotational convenience. Then you can take the 0th layer. Let's get it as 0th layer. This is the first layer, second layer, third layer, goes on up to nth layer. It's an n layer format. So deep learning network looks like this. An n layer format. All deep learning network looks like this. Okay. So this is the first one, Z1. Is it clear? What's happening here? Can somebody explain? What is it? Red line indicates? What is this notation, man? Can somebody tell me this notation clearly? What is this happening? Asha? Am I audible? Akash? Abhijit?
Yes, sir.
Abhijit, Varsha, yes. Can you explain this? What is that one?
The weights are getting multiplied with the inputs from various, and then they are getting the summation.
Okay, where it is all happening?
Sir?
Where it is happening? Which particular node it is happening? All this.
And Z1.
It is at the Z1. Okay, first node here. Okay, that's the first node F1. Okay, and what you have computed right now here is the pre-activation function value for the first node.
First layer.
Yeah, first layer. Okay, first layer. That's important. Yeah, this
first layer means then it should be from for all.
See the 0th input now, the 0th layer. Now, this one is called as the 0th layer. Whereas can you see my this one? This is a 0th layer. 0th layer means you have all these values, all these nodes. First, this is first layer. This is second layer. This is third layer. This is fourth layer. It goes on nth layer. So I'm talking about a layer means it consists of so many neurons inside. Okay. So that is this bracket 1 indicates the superscript na here 1 that indicates whatever is going to happen at the first layer. In the first layer, you have first node is given by Z1. Okay, that's a Z1 pre-activation function you are computing. Okay, then once you compute the pre-activation function, that should be passed through a function. That function is the log sigmoid function. Is it all right, Varsha? Do you understand what I'm saying?
Yes, sir.
Now look at this. I see it now clearly. That's what we said now, right now. Now this is what is happening. What is this Y1 indicates? YJ1. What is that?
Output after the activation functions.
That's the activation. After passing through, after you compute the pre-activation function, you have to pass it through the function. Okay, that's what F1 EZJ1 indicates. Then what do you do? So you take that, okay, and pass it to the second layer. So now it's been changed. See here, it's been changed. Initially we are starting at the first node. Then I'm doing it for the jth node. Any one of these nodes. All these nodes you have to do all this first layer. That's why ZJ of first layer. You have to compute all this for all these nodes. That's why all this red line comes. Can you see it? Neatly given. If this is the one, red layers, first node only. Now when I do this, you can see first node for all the nodes you are computing. Okay, that's what this did. Now you do it again. This is for Y1. Okay. Now you do it for all the nodes. Compute. Okay. Compute for all the nodes ZJ2, second layer. Pre-activation function for the second layer. You have to compute that. Then you pass it through this layer. Is it clear now? So what we are trying to do. Okay, so now you do that.
Sir,
Yeah. Yeah.
what
Please.
is that one, sir?
Which one? This is one. This one indicates the first
No, sir,
layer.
in the diagram, red below down,
Is it
sir.
bias, sir?
That is a bias. That's a bias. Okay, that one indicates because you have to see understand that even though you put one there, the input is always one there. Okay, but there are weights associated with it. Okay? You need to compute that weight also. So that's why
They
in the
didn't.
input layer you need to put n plus one. I said, remember what you what? No, you
No,
said
sir,
something.
they didn't add bias like weight into input plus bias. They didn't do. Is that one
Yeah,
related
that's
to
what.
that?
Instead of that, they add that weight also. They put that inside this particular summation. We already
Okay.
learned. Okay,
Yes.
WO,
W
in
naught.
fact, yeah, W naught is what, in fact, that way they put it. So that's how it works. Okay, now ZJ3, YJ3, you have to compute pre-activation, activation. Okay, is it clear? So this is called as the forward computation. Called as the forward computation. All right. And you see it, how we are doing the forward computation. This is important. Once you compute the forward computation, okay, you can do this in terms of simple kind of a code. Okay, we'll see the code later on, but just get a feel of it, what we are trying to do. So we have computed all these intermediate values in the forward computation. You must remember them, we will need them to compute the derivatives. Now we are going for the final output. The output is compared with what? The desired value. All right. Arun Balaji, Bhaskar, Bhaskar. Are you getting the point clearly? What I'm trying to
Yes,
convey
sir.
to you? Okay, it's an excellent slide again. So look at this. Conditions clearly given, neatly. Okay, now you have to compute Y of it. So this is Y of it. What is this? Is we are at this point, we are going to compute the change in this error, okay, the divergence error, with respect to this Y of n, okay, the derivative. We then compute with respect to Zn. Okay. What is Zn? That's the pre-activation for the output layer. What is Yn? That is the activation at the output layer. a function after passing through the function, it's going to, something is going to come out. Now that is yn. So you are finding out the error dou e by this dou yn first, and then that has to be passed through zn. Okay, the error, how this error is going to change with respect to zn, pre-activation of the zn using the chain rule. Okay, and then you need to modify this weight c here. How these weights are going to influence this zn, you have to see that. And then this, keep moving. Can you see it from zn to yn minus 2? Zn minus 2. It keeps going. The backward one, along with that weights coming into picture. And then yn minus 2. Zn minus 2, y1, z1. Can you see it clearly? This is the first stage. Compute this chain rule. You are applying the chain rule. Gradually you are taking in backward. The error is back propagate like this. Every stage pre-activation, activation. You have to find out the derivative. Every stage. Okay? That's how it operates. The computing the derivatives is what we have learned. Okay, so this is different notations is used, but anyway, it's almost similar. Okay, exactly same whatever we learned in the last class also. Now the same thing. Dy dou y by yan. Okay, you have compute this. This is already computed. Okay, dou difference by dou yan. This is nothing but what? This is a final activation function. Activation function by the corresponding dou z1. That's nothing but the derivative of the activation function. Whatever pre-activation function is there, it passes through a function. Okay, that function is the logistical function, so which is nothing but the derivative of that function with respect to that pre-activation function. You understand here? What is y1n? Can somebody tell me what is y1n? Nth layer activation function after passing through the function called a log sigmoidal or tan sigmoidal. Z1n, that is a pre-activation function for that layer. So when you are finding out the derivative of that, this derivative, in fact we derived this 1 by 1 plus exponential of that one. We derived that, and if it is equal to f of x is 1 minus f of x. We derived it using Mitesh Khapra's lecture. I hope you can recall it. So that is this derivative. Okay. So this, so can somebody tell me for a squared error what value you obtained for this? Dou did by dou y1n. Can you recall? For the squared errors, what did we obtain? The last class we learned now.
2 into the difference. The error.
1 minus y, 1 minus y cap. Very good question. 2 into the y minus y cap. This is the corresponding. Okay, so you have to understand this clearly. Computed in the forward pass. This is z1n. So naturally you can substitute it and you can get this value. Then you have to move. Okay, then you have to find out what is the value of the derivative divergence with respect to z1n. That is what this value obtained. And that's for all the modes you can compute. See here, one more for all the modes. That is this. Then you move on to the weights. Okay, what is this? The error with respect to this weight set of weights. That is nothing but dou z1 by dou w11. Okay, dou z1, the nth layer, for w11 for the nth layer. Okay, and then dou divergence by dou z1 for the nth layer. This is already computed. Okay, just to compute previously. See here, this is what we computed, and again use that. Just compute. Now use it again. This you can compute by using this method. Okay, computed in the forward passes value, you can use it. So it goes on like this. Already computed, it goes like this. Going back. Okay, by stage. So that's the backward pass expressions. Okay, this is something you need to look into. Forward pass, backward pass. So that's this algorithm. Okay. Now, take this problem. A very simple example is given. This one is taken from CS231, already which I mentioned to you, lecture CS231 by Stanford University's back propagation. This is the one. Okay, I'm using that. But this, try to understand this. A very simple example: f of x comma y comma z is equal to x plus y then into z. This is a function. Okay, x equal to -2, y equal to 5, z equal to -4. So in that case, we are doing something called a back propagation. A very simple example. What is q? Q is equal to x plus y. Okay, then what is dou q by dou x? That's going to be 1. Okay, it's quite obvious. Do like a scalar case. Okay, dou q by dou y is going to be 1. And the f is equal to q z. Q into z. This f. So what is the function? X plus y into z. I'm splitting this into 2. I'm computing initially x plus y and then multiplying with z so that I'll be getting this f. So I'm doing the partial derivative here. I'm doing dou q by dou x. Here I'm computing the gradient with respect to x. Dou q by dou y I'm computing for y. And then dou f by dou q is equal to what? Is equal to q into z. You agree? Q into z is f. Therefore, dou q by dou f by dou q is going to be z. Dou f by dou z is going to be q. Is all right? You agree with me? Correct. Okay. So what do you want to compute? We want to compute how this one is going to vary f with respect to x and y. X, y, and z. Individually, you want to know. What you have right now? Dou f by dou q you have. Dou f by dou z you have. Okay. So, but you want to compute dou f by dou x and dou f by dou. So you're trying to relate that. How do you do it? Using the chain rule. Okay, using chain rule you can do it. Dou f by dou x equal to dou f by dou q by dou x. Okay, notice this. So this is the condition initially. So initially dou f by dou f is equal to 1. Okay. Then what do you do? You work out dou f by dou z. You can compute that. That value is going to be 3. Why it's 3? It's obvious, okay? Dou f by, here it is. Dou f by dou z. Dou f by dou z is equal to 3. Why? It's going to be equal to q. What is q? -2, x equal to -2, y equal to 5. Therefore, it's q equal to 3. Therefore, dou f by dou z is equal to q. So at this point, the gradient, okay, based on the small change in f, in order to get a small change in f, the change in z required is 3. That's the idea, the gradient. Okay, so that's a gradient. It's a positive gradient. If it is changed by 3 units, there will be a change in 1 unit here. That's the idea. Okay, dou f by dou z. It is obvious. Can you understand it clearly? Anyone? -4 into 3, what do you get? 12 minus 12. Okay, is it clear? Therefore, a 1 unit change here, 3 units change here. That is this idea. Dou f by dou z equal to q. That's what this 3 indicates. F is equal to q into z. Q into z. Q into z is what's happening here. Okay. What is then? What is dou f by dou q? What is dou f by dou q? Can somebody help me out?
Z.
What is that? Huh?
Z -4.
-4. You have to understand that clearly. See, for a small change, for example, in order to bring a 1 unit change here, I need to multiply 3 by -4. Then only I get -4. You understand? So, in order to get -12 here, -4 into 3 I did. So that I got -12. 1 unit change. Okay. So that is the idea. So that is the concept. Okay. So that's what we are doing. So -4 is the corresponding gradient over here. So then we have to back propagate through this addition, summations. When summation comes, you should be a little careful. So what is dou f by dou y? Dou f by dou y, you need to compute first dou f by dou q first. Are you seeing it clearly? You have to compute that, and then that dou q by dou y is what you need to compute afterwards. Dou q by dou y, here it is. The value is 1. Okay, so dou f by dou q is again the same value, -4. Is it clear? So how we are computing this? Krishna, Puja, I repeat. Gurupuran,
Sir, என்னுடைய டைம் ரிப்பீட் பண்ணுங்க
repeat
சார்.
பண்றேன். கவனி.
லைக் கொஞ்சம் கண்டிப்பா
இது
சார்.
முக்கியமான ஐடியா. இது பாரு.
ஓகே சார்.
இது வந்து ஒரு ஃபங்க்ஷன் f of x, y, z is a function. X plus y into z அதான் ஃபங்க்ஷன். அது என்ன பண்ணிருக்கோம்? We are splitting it. The professor from Stanford has split up, in order to explain, he has made it like this. So x is here, y is here. You add these two, you go to get that one. Then z is here. So it is like this. So I'm going to multiply x plus y q into z. So I get the function like this. So we are interested in computing the gradients. Okay. So I want to see for q, I know this is x plus y. So if I find out dou q by dou x, the value is 1. Dou q by dou y, the value is 1. So then the function f is equal to what? Q into z. Okay, you agree? You see it, Krishna. Q into z is a function, this output function. Q is what? X plus y. What is z? Z is equal to the same z. So f is equal to q z. Dou f by dou q is equal to z. Dou f by dou z is equal to q. So what do you want to compute? We want to compute dou f by dou x, this one. See, you are passing through one hidden layer. That's the idea. Okay. This is the output layer. This is the hidden layer. This is the input layer. So I want to pass through the hidden. How we are going to compute the hidden? That's where the chain rule comes. See here, dou f. Maybe you can see this. You understand? So I'm starting from dou f by dou f. What is that value, man? Dou f by dou f. Krishna. Value is 1. Okay, anything differentiation. Small change in f, small change in f. So it is value is 1. The gradient is 1. Now I'm going for dou f by dou z. What is this value?
So Q sir. So Q value is 3.
Correct. Dou f by dou z is q. Q is equal to what? 3. That value is this 3. Then what you are understanding from it? See, in order to change, bring about a small change here, okay, in order to get this minus 12, the corresponding gradient here is 3. So 4 minus 4 into 3, I can get minus 12. You understand? So for 1 unit change, okay. So that's what this idea is. Now what about this one? Dou q by dou f by dou q. What is that? It should be dou f by dou x. That should be minus 4. Then only you can get minus 4. Is it clear? Yeah. Now, but you have to be careful here. The plus, in fact, is a different thing. You should be. You should be. See, this is a direct gradient you have computed so far. These two are directly connected to the output layer. But the next two na x and y, you are passing through this hidden layer. Okay, that's where the chain rule comes. See here, dou f by dou y I am going to compute. So what I did initially dou f by dou q first, followed by dou q by dou y. It's already computed 1, that value. So that should be minus 2. Is it clear? The same manner you can work out dou f by dou x the same way. Dou f by dou q first, from here to here we go, these two. Then from that to okay, dou q by dou x. So that's the chain rule idea. So that's basically the idea, in fact, he is talking about. So you have the local gradient. Local gradient means what? Here, what is the local gradient? Dou q by dou x, dou q by dou y. Okay, they are the local gradients. Now, when you are going to pass from the output layer to the input layer, dou L by dou Z if I want, for example. Okay, this is dou L by dou X. In order to compute dou L by dou X, okay, I need to know first dou L by dou Z, that one, followed by dou Z by dou X I should. That's the local gradient I should. Okay, is it clear? Is it clear? This is x, y, z. Okay. These are all the gradients I am interested in. Dou L by dou Z I computed. Having understood the dou L value, dou L by dou Z, I am interested now in going back to the previous layer. Okay, predecessor layer. So in that case, x and y, I am going to use that gradient, but multiplied with a local gradient. That's important. Dou Z by. In this case, if you look at, I computed dou f by dou q first, and then multiplied with the local gradient, dou q by dou x, in order to get dou f by dou x. Same idea. Is it clear? So back propagate. That's why it's called back propagation. So now look at this bigger case. If you look at this case, maybe you can gain some interesting insights. Maybe you can go through this. You see here, the professor, what he has done is he has taken this function and this has split open this function into number of terms. Can you see the terms? W0 x0 first term, W1 x1 second term, W2 third term. So then you have to add these three. Yes, multiplied W0 x0. There are two multiplications, one addition, one more addition here. Okay, and then minus of all those values, that's minus. Then pass it through the exponential function, then add 1, and then take the inverse of entire thing, 1 by x. So yes, made it more complicated function. Okay, it's very simple direct tan h function, sigmoidal function. We made it so in order to understand the back propagation idea and better insight, with better insight. So this is a function we are interested. Okay, so for you know that f of x is equal to ax means dou f by dou x equal to ax. F of ax equal to ax means dou f by dou x equal to a. F of x equal to 1 by x means dou f is by 1 by minus 1 by x square. F of x equal to c plus x equal to dou f dou x equal to. These are all the derivatives of some simple functions. So simple functions what we are chosen. So all these are very simple functions. So here first thing is we are going to compute this here. Okay. So let us start with it. Okay. So what is this value? Minus 1 by 1.37 square. Why it is 1.37 square? That is the input. Okay. So this is the into 1. Okay, into 1 is going to give you the minus 0.5. That's the gradient first one you are working. Local gradient. Is it clear? Why I am doing that? In order to compute this dou L by dou Z. Dou L by dou Z is 1. Okay, this final value is 1. Here. The first one. That value is 1. When you find out the derivative of the same function, dou F by dou F, that's going to be 1. Okay, then I'm going to pass that through inside. How I'm going to do it? I have to compute dou L by dou Z, multiplied dou Z, that is dou S by dou X, and then multiplied by dou L by dou Z. In order to do that, I'm doing this. So this is what I'm doing, 1 by X. See? Dou F by dou X, minus 1 by X square. That's what we are doing. Minus 1 by 1.37 square into the previous gradient, 1. That's going to fetch me minus 0.5. So the gradient at this point is going to be minus 0.5. Now in this, when I'm going to compute for the next one, what will be the gradient which we have already computed? That's going to be minus 0.53. I'm going to use that for computing this gradient. See how I'm going to do it? It's going to be a simple plus 1 factor here. Plus 1 factor means out of this 4, which derivative? This one. Okay, plus 1 factor. So this one. Okay, dou F by dou X is equal to 1. Okay, so naturally, I'm going to have what? 1 into minus 0.5. Okay, you understand? How many of you understood? Can somebody explain this first one? Guruparan?
Yeah,
Tell me what is this first one?
sir, back propagation புரிஞ்சு sir.
What is that you understand here? 1 by x ஒரு function இருக்கு, அதுக்கு ஒரு input இருக்கு 1.37, 0.73 தான் output. So the gradient of output with respect to output என்ன 1. சரியா? I am going to pass on that gradient to the input level. So for that, this is a function. Okay, 1 by x தான் function. 1 by x function, when you are finding out the derivative of it, what do you get? Minus 1 by x square. You understand?
Yes, sir.
So for x is what here in this case 1.37. So minus 1 by 1.37 square into the gradient what you have computed in the previous year. So you understand this? So for example, in order to compute dou L by dou X, what I did, I used this gradient. Dou L by dou Z into dou Z by dou X. You agree? The same manner here I'm going to do. Here what I have? Dou F by dou F I have. In order to compute dou F by dou X, what I am doing? Dou F by dou X, okay, into dou F by dou F. That's going to be minus 1 by X square. So that's what this value is, into 1. Dou F by dou F is equal to 1. Okay? So this is dou F by dou X I have computed. That's going to be minus 0.5. So for the next one, if I'm going this for this one, how do I compute? I'm going to use this gradient, whatever I computed, pre-computed, to compute this gradient. How I'm going to do it? For a constant number like this, what is the derivative? 1. Okay, dou F by dou X is going to be 1 for the constant derivative. A constant number, plus 1. Okay, so it is more like C plus X. The function is more like this, C plus X function. Okay, so dou f by dou x equal to 1. So is it clear? 1 into the previous layer, yeah, the already pre-computed, minus 0.53 you plug in, I'm going to get the same value here. The same value here. Okay, so here you should not think that how do I compute the derivative of a constant? Derivative of a constant is equal to 0. But the key point is, whatever that you are causing it here, it's going to get added with 1. Keep that in mind. Plus 1. So naturally, some value, this is x plus 1. That's the kind of expression I'm talking about. So naturally, it's going to be df by dx equal to 1. That's the derivative we are talking about. X plus 1, that is the function is happening. Okay? Is it alright? Everybody with me? This is x. Okay, x plus 1. That is the function here. Don't think it is plus 1, it is constant, so derivative will be equal to 0. It is c plus x. C is 1. So 1 plus x, that's the function. 1 plus x, what is the differentiation? 1. So whatever it has happened over here, that's going to come over here. Minus 0.53, minus 1. This is back propagated without any much of change. But if it is value is going to be plus 2, what will happen? 2 into minus 0.53 is what the idea is. No, that is 1 only. Okay, it will not be changing. Even if you add any number here, plus 1, plus 2, plus 3, you add any number, this value will not change. Minus 0.53 will be passed through this plus 1. Is it alright? Everybody with me? That value will be there. Then you go for this. Now this minus 0.53, I'm going to use it here. How I'm going to do it? Dou f by dou x equal to ex. So naturally, ex, I'm going to substitute for this minus 1. Minus 0.53 is the previous layer's gradient. I'm going to use it, multiply, I'm going to get this. Okay, that's how it operates. Okay, same way, 0.2 is used here. Minus 1 into that. Minus 1 is that value into that. Whatever a is there, you're going to get it. Ax it is. Minus 1 into x. X is also 1. Can you see it? This is into, this is plus. Remember that. For both the values, dou f by dou x equal to a. I'm going to have a here. Therefore, a is what? Minus 1. Minus 1 into the previous gradient, minus 0.20. Multiply, I'm going to get 0.20 as my gradient. Okay. Same manner, you have to proceed. Okay. So I'm going to use the previous gradient's values. Okay, 0.2. Okay. So into this. 1 into 0.2. 1 into 0.2. 0.2 for both the equals. Will be passed on directly. So directly you are passing the gradient through plus sign. Okay. And then here 0.2. Okay, 0.2 into 2. This is minus 1 into 2. 0.2. So you got minus 0.2 minus 0.2 from the 0.4. It's all right. You have to understand this. All right. Look at this case. This is directly you're passing. Okay, through the positive sign. 0.2, 0.2 both split up like this. Okay, local gradient into upstream gradient. Local gradient is 4.2. Okay, directly passed, and this one, you see, this is 0.2. This is output end. These are all the two inputs. Okay, therefore 2 into 0.2 going to give you 0.4 here. Minus 1 into 0.2, it's going to get minus 0.2. That's what we learned there. We addition a product, when we worked out the product, in fact, we did something like that one. See here, when you did the product, dou f by dou q equal to z, dou f by dou z equal to q. So then you did this. Okay, remember z and q. The same manner here. There is a product here. Dou f by dou x naught is equal to w naught you are going to get. Dou this one you are going to get. Yeah, for this one you are going to get 2 into 0.2 for x naught. 2 into 0.2. It is 2 into 0.2. Okay, and this one is going to be minus 1 into 0.2. Previous lines. Okay, minus 0.2. So that's how it operates. So this is a sigma order function, and you have to remember this idea. Okay, dou q by this, dou f by this one. if I differentiate this once with respect to x, I'll be getting this 1 minus sigma x, x sigma x. This is f of x. In fact, we derived this. I hope you can recall this. Okay, so go through this again. So what is the key point you are taking from this slide? Can somebody tell me? The output is going to be 0.73. Input is equal to 1. If I'm going to give feed 1, I'm going to get 0.73. What is that? The gradient then will be what? 1 minus whatever be the output of the function, okay, 0.73 into 0.73. If I do that operation, I'm going to get 0.2 as a gradient for this particular sigmoidal gate. Okay. So sigmoidal function, whenever you use, you can directly compute the derivative without using any method. You simply put 1 minus f of x into f of x. You're going to get the derivative immediately. Okay. Then based on the output, you're going to compute. So we'll see all this. Okay. Local gradient. So matrix form it is given. We can see some other class, but the codes are there. Okay, you can work out with the codes of this slide. They're also local gradient. So this is what we learned in last class. And we go through it again in order to gain more insight. So we'll work out a problem for next week. But derivation, you please go through it completely for the forthcoming test. Okay. So one question is out. We can go through the derivation part completely, back propagation. We are going to write that derivation. 10 marks. Totally, the test is for 50 marks. Okay. It will be converted to 10 mark finally. So there will be 5 questions, mostly analytical, 90% analytical, 10% maybe one question. Yeah, one question is more of derivation kind, back propagation derivation of derive completely. Then some problems. So whatever problems we have seen so far, the conceptual ideas, we go through it. The algorithm is asked to write the algorithm. Okay, that's all. So we'll meet in the next class. By Monday, be ready. By afternoon, what time I said the exam? What time the exam? Bhaskar.
12 to 1, sir.
12 to 1:30. Okay, we'll keep it. 12 to 1:45, we'll keep it. 15 minutes for uploading. The test is for 1.5 hours. Okay.
Sir,
Yeah.
11 to 12 free, sir.
Then okay. Then keep it. Start by around 11. 11:30 we'll start. We'll finish it up by 1 o'clock.
Yes, sir.
11:30 to 1. Okay. All right. Anything you want to modify? Yeah. Do it comfortably. Okay, no problem. So this paper, 75 marks is for project. Okay, so try to concentrate more on the project. Try to think about a good project, how to develop it, how to present it, how to come up with some good results to explain to somebody. Yeah, all this you have to plan. So then you get a very good grade in the subject, no doubt. Okay. Fine. With that, I'll stop. Anything you want me to ask? Anything you want me to ask? Right. Thank you.
Thank you, sir.
You can go through all these videos. See Professor Bhiksha from CMU, Okay, his video is available. Videos of Mitesh Khapra is available. So videos of the CS231 just now I have shown some slides. That is also available. 2017 lectures are there. 19 is not there. I think. Go to check it. 2017 is alright. Okay, we are lagging. Okay, we can catch up. So we can go through that lecture also. So you can make it clear that when you're going to work with an algorithm, one particular algorithm, you should be in a position of writing a code as well as getting a deeper understanding about it. So that when you are presenting or when you are talking about that algorithm to somebody, you feel much more confident and clear. Okay, so try to spend some time. Any algorithm you want to work, spend a lot of time with it. Try to dissect it, open it up, and see what is happening inside, how it is operating, okay, what are all the significance of each and every parameter inside. So everything you need to gather information. Okay, so it's more like okay, let's stop here.